Hello, I'm Trent Rosenthal, and this is going to be another episode in the Qubi Programming Language series. This one should be a little bit of a brief one, but we're going to be talking about the parameterized gates. So if we go ahead and open up the Qubibyte Quantum Circuit Simulator, which is available at qubibyte.org/simulator, then we can go ahead and see that we have all of these gates, and you can't really tell which ones are parameterized from the side unless you were to sort of look into their information, but I can just tell you straight away the ones that are parameterized would be the phase gates, and we've discussed a few of these in the last video, but the phase gates, the RX, the RY, RZ, U, which has 3 parameters, as we've talked about, the controlled phase gates, so now we're getting into the multi ones, which will be the main focus of the next video, but the controlled phase gate is the sort of the last built-in gates that has parameters, and of course we can also create our own. That will be a separate video, which you can see in the playlist, but just going off of the built-in gates, as we go ahead and place this phase gate, we can go ahead and set the parameter to whatever value we want. As you can see, that equally changes it for the pi radians, for the radians, and for the degrees. So if we go ahead and set this to, say, 270 degrees, you'll see it won't make a difference yet. And that's because this is a phase gate which rotates in the phase plane, which is the XY plane, this plane with the red and green line. But because it's at the 0 state, it actually appears to be making no difference to the gates. And so here's another error in this quantum circuit simulator that we're going to have to fix, but that's all right because we can just vibe code it and fix it pretty easily. But that's probably why this error exists as well, because it was vibe coded. But anyways, if we look at the phase gate, we can see that we have a 1 in the top left and then the phase in the bottom right. And as you can see, that's what happened when you ran the circuit and maintained the 1. So this visualization and the data analysis is wrong, but the result is actually correct. It should be a 1, 0. And if we go ahead and apply an X gate to this before, should see, yeah, now it's 0, negative I. So this very matrix in here is wrong. By the time you watch this video, it will be correct, but the matrix in the actual gate is correct. But yeah, it would be expected that if we were just applying the phase gate, it would be a 1, 0, and if we were not applying it, it would be a 0, negative I. And as we talked about in the last video, we can factor out that negative I actually, because we can say, okay, a negative I is the global phase, so negative I times a column vector of 0, 1. So that negative I actually doesn't matter at all, which means we now just have the 0, 1 state vector, which is in the 1 state, which means that the phase gate pretty much was meaningless for at least this example. If we go ahead and comment out the phase gate with a double slash, which comments, we can do a double slash. We can also do a slash asterisk if we wanted to do like a multi-line comment. But anyways, if we go ahead and comment that out, you can see it actually makes no difference because the 0 and 1 basis states are eigenvectors of the Z gate, of the phase gates, of, S dagger, S, T, T dagger. It is a eigenvector of all of them. So when you try to apply phase to it, it won't really matter. I mean, you can kind of visually see how could it matter if you try to rotate this in this direction, but it's already lined up with the blue line. It wouldn't really rotate at all except for having a global phase. So that's just one example of the parameterized gates. We can see the default way that it's written is P space 0 space 1.5. This is when the parameters would start, is after the qubits that it's being applied to is defined, which we can also do like 0, 1, 2. We can do just like 0, 2. We can do like a 0.5 if we wanted to apply to all, or do a step size of 2. So there's a couple of ways that you can write this. We can also just write the 1.5 in parentheses attached to the gate and then do a 0. You can also say maybe we don't want 1.5 pi radians, maybe we want 1.5 radians. As you see, that changes. So the gate displays as 270, and we can change that in our settings if we wanted to. Displays as 270, which is equivalent to 1.5 pi radians. We can also do 1.5 rad or rads or whatnot. We can do 1.5 degrees. So those are pretty much the big 3 ways of writing the parameters. We can do pi radians, or degrees. And instead of just doing phase, you can do RZ, which actually we should go ahead and put this in the superposition Hadamard gate state. So you can actually see it making a difference. If we do 1.6, well, that's not going to be very visible, but if we do like 10, you can see it start to make a difference. 100 does a lot more of a difference. And here's a little sneak peek at variables and sweeper variables, which we'll discuss in a future video in the playlist. We can set, let's just come up with a variable name. Let's do rotation amount. That's obviously going to error because we haven't defined it yet, but if we do rotation amount equals 5, it will set it to 5 pi radians, which let's actually just do degrees. Or for a sweeper variable, we can do these little triangle brackets, and we can do 1 ... 100 degrees, and that sets it so in this current circuit it's only 1 degree, but we actually have 100 versions of this same setup, and all of them differ by a little bit. And if we go ahead, and here's maybe a cooler way to do this, we can do it as an RX instead, get rid of this Hadamard, and do maybe, we'll do 0, 10, so step size of 10, 360 degrees. So if you look at the block sphere, every time we go through one of these circuits, it rotates by 10 degrees around the x-axis. So we'll set this back to 0. Parametric sweep, you will see a full detailed video on, but if we go ahead and just click run full sweep without changing any of the parameters, it will actually run all 37 of these circuits. And in this case, we just have it set to, it will tell us the probability and plot it out of it being in the 0 state, which as you can see follows that same pattern. So it will start with 100% chance, then you rotate 10 degrees, it becomes a little less of a chance, and over time it reaches, should be 0. Okay, maybe it's 5.29 times 10 to the negative 29. It will reach 0%, and then it loops back up to 100%. So that's a little bit interesting thing that you can do in a Qubi that would be kind of hard to set up in other quantum programming languages. But if we go ahead and remove this, set this back to like 50 degrees, we can see RX, again, 50 degrees around the x-axis. We can do RY for 50 degrees around the y-axis, RZ for Z, as we've talked about. The 0 state is an eigenvector of the phase-related gates, so you won't actually notice a difference, but it will differ in its global phase. The last gate with parameters that we will talk about is the controlled phase gate. As you can see, it's the same matrix as the phase gate, but this one has a control. And in the following video, you'll learn about what exactly controls are, how they can be used, as we talk about all of these ones as well. But if we go ahead and drag this gate somewhere on here, you can see there's currently no room for a control because we only have 1 qubit. So we need to add another qubit to the circuit, or we could have also just dragged this one here to generate a second line, drag the controlled phase gate here. There's only 1 line, so it's selected by default, which is qubit 0, which is what we're setting the control to. Now we need to set how much it can rotate in the phase plane. So if we go ahead and set this like 150 degrees, this phase gate will only apply to the Q1, which we can go ahead and see the block sphere here. It will only apply to the Q1 if this control is activated, and this control activates if Q0 is measured to be a 1. And right now, since we've put nothing before it, it's just going to be 0 by default. So if we go ahead and put an X gate before it, we can see that this X gate makes this Q0 become a 1, which you can see here, which now this control will trigger and activate a phase gate to Q1. As you can see, there's no difference because Q1 is in the 0 state still. So if we go ahead and apply a Hadamard to Q1, and if we do this step by step, you can see it will flip. So it goes to the plus state, and then we go to the second step where this control activates, this phase gate applies itself to Q1, it rotates 150 degrees and ends up in this position. So that was the tutorial on how all the parameterized gates work. There's actually one that I did mention, which is the U gate, which we touched on in our last video. But if we go ahead and move all of these around, we can do the same example again where we set the first parameter to pi, the second to 0, and the third to pi radians, and then hit confirm. And as we saw, that does the same action as the X gate, because pretty much all of these gates can be made out of just this U gate, which is a universal gate. Pretty much all these gates can be made just by setting these 3 parameters here. So we set those, it does the same thing, it flips it from the 0 state to the 1 state. Pretty interesting, a little bit hard to use, not very intuitive, but you know, as you advance your knowledge in these quantum circuits and quantum algorithms, maybe it becomes a little bit useful. And you know, that's pretty much what we have for this video.